Okay, so here we're going to look at a problem called the conical pendulum, which is one of the sort of classic Newtonian mechanics problems that you'll see in a lot of those courses. So it's called the conical pendulum. So we'll draw a little diagram of the setup here, and we'll then sort of analyze it a little bit and figure out what we want to figure out about it. So we've got a pendulum. You might be familiar with your standard sort of pendulum that swings back and forward, and you know, in a lab or in a lecture module you will try and figure out what the period of that pendulum is. Well, we're going to modify it slightly. So instead of the pendulum just going back and forward, this one is going to move in a circle. So sometimes when you're sort of playing around with a pendulum, actually let me make that circle a little bit bigger. Sometimes when you're playing around with a pendulum, you accidentally send it in a circle. Well, in this case, we're sending it into a circular orbit deliberately. So that circular orbit is going to have a radius r, which we can draw in here, and it's going to have a length L. So the length of, where it's hinged to the center of the pendulum bob is going to be L. And the question is, what is the period of the rotation? So basically, how long does it take for our pendulum to do one orbit? And we'll call that t, small t. So we're gonna put in a couple of things that we know about the pendulum. So let's just say that the length is 50 centimeters, and the angle that the pendulum makes with the vertical is 35 degrees in this case. 35 degrees. So we know the length, we know the angle that it makes with the vertical, and we can draw that in now. So yeah, we're still in blue. So we go here, and this angle here is our angle alpha, and that's going to be equal to 35 degrees. So this is a case where we need to look at the x components, the y components, and the fact that the pendulum is moving in circular motion to try and figure out can we figure out the period of rotation from that. So we're going to need to do the balance of forces and look at it from that point of view. So first of all, we're going to look at the y direction. So in the y direction, what have we got? Well, if we look at the pendulum in the y direction and the forces associated with it, so let's sort of move it over here just to keep our diagram clear here. So let's now imagine that the pendulum is here and the string is holding it in place. So it's moved slightly. Well, what have we got in terms of forces? Well, we've got the weight of the pendulum acting down, obviously, so that's going to be mg, and that's balanced by the tension in the rope. So if the rope or if the string wasn't there, the pendulum bob would fall to the ground. So there's some force holding it up to do with the tension. Now it's only going to be a component of the tension force, so the overall tension force acts in this direction. So this is our resultant tension, if you like, and that's made up of an x component and a y component. So that's the y and that's the x, and this we're going to call t. So then the length of the y component is going to be t cosine alpha. So this angle here is also going to be alpha, just because of similar triangles. So in the y direction then we've got t sine alpha acting downwards. T sine alpha, acting, let me try it again, t cosine alpha, my mistake, acting upwards. And we've got mg acting downwards, and those two are equal because the pendulum is in equilibrium in the y direction. Or we could rewrite that then as the tension is just equal to mg over cosine alpha. Now the x direction or the x component doesn't really tell us anything, so the next thing we're interested in looking at is what can we gain from realizing that the pendulum is in circular motion. So in circular motion, in the x plane, if you like, in circular motion, what have we got? Well, this guy here is going to be t sine alpha. So it's that component of the tension that's keeping the object moving in circular motion, if you like. So that's the centripetal force in this case, is this the horizontal component of the tension. So that's going to be t sine alpha, and that then is, as we said, going to be equal to the centripetal force on the system. So that's m omega squared, or just from the definition of how we define centripetal force. And we can call these two equations 1 and 2 because we're going to need them a little bit later on. So what can we tell from that then? We can say, let's see, we can set up an equation here, first of all, before we continue, that sine alpha is equal to r over L. So the idea here is we want to get rid of, we want to solve for t eventually, basically. So sine alpha is going to be r over L, which we can see from the right angle triangle on the left there, where we've defined L and R. So that should be straightforward enough. And then omega, which is the angular velocity of our pendulum bob. Well, its angular velocity is going to be governed by how long does it take to do one rotation. So one rotation is 2 pi radians, and the time it takes to do that is going to be t, which is what we're trying to solve for. So up in green there, we've said what is the period of rotation, and we're calling that t, so that's small t. And we're going to take g is equal to 9.8 meters per second squared. So now let's see if we can do anything with these equations 1 and 2 that we've looked at there. So we've got, if we take equation number 2, what's t sine alpha going to be? So t sine alpha is going to be, well, t first of all is mg cosine alpha. So let's show you what I'm getting at here. So we'll take a red line here. So we've got a t. So t we've defined in red above there as mg over cosine alpha. So we got that from equation 1. And that's going to be multiplied by sine alpha in this equation. And sine alpha, we said, just one line up there, is going to be equal to r over L. So that's equal to r over L. And that then, that t sine alpha is equal to m omega squared r, which was the centripetal force, m omega squared r. So m omega squared r, from our definition of omega being 2 pi over t, that then becomes 4 pi squared. So we square the 2, we get 4, we square the pi, we get pi squared. And then we have our m from equation 2 and our capital R from equation 2. And all of that is going to be over t squared because we have omega squared. So this equation here comes from this point here. So now, let's just, we're looking at the two sides of this equation. So we're looking at the left and the right hand side. Now we have an m on both sides, which we can cancel out. We have an r on both sides, which we can cancel out. And now we're in a position where we can solve for t. So t in this case then, just a simple solution then, t is going to be equal to 2 pi times the square root of L cosine alpha over g. Now, if we analyze what's going on there, what we see is if alpha is equal to 0, then cosine alpha is equal to 1, and we basically get the result for the simple pendulum. So if cosine alpha is 1, we then get t is equal to the square root of, 2 pi times the square root of L over g, which is the simple pendulum result. And that, that should make sense. That's consistent with the model we built up. If the angle is 0, we just have a simple pendulum, and the equation collapses to the original one. Now the question we set out, we're not quite there yet. We said that we're looking for the case when alpha is equal to 35 degrees, and that gives us then a t of 1.285 seconds. So the period of rotation of this conical pendulum is 1.285 seconds. And we can see then, so as the angle goes up, cosine alpha is going to go down, and that means that our period is going to also go down as the angle goes up. So if we've got some sort of extreme case here where, you know, the pendulum is at a very large angle with respect to the vertical, in order for this guy to move in circular motion here, basically he's going to have to move very fast to maintain that angle. So that's the basics, you know, the derivation of the conical pendulum. Pretty straightforward. It just requires you to do your balance of forces both in the y direction, where the vertical component of the tension is balancing the weight, and in circular motion, where the x component of the tension is the centripetal force, which keeps the pendulum moving in a circle.